So I just want to take a few minutes to go through this other curvature formula. I didn't quite get to it in today's lecture, and it's likely that some of you will be working over reading week and maybe encounter some questions where this will be useful. So I want to make sure that I at least take the opportunity to show you this last curvature formula, which is, of all of them, probably the easiest one to use, and to do an example where I illustrate how to use it. So the reason for, so I say this is the easiest one to use. You might be looking at it and going, well, that looks more complicated than the previous one. And here was our previous curvature formula. The curvature was the magnitude of the derivative of the unit tangent vector divided by the magnitude of the tangent vector. That one, the reason it's a little bit more complicated to use is because if we look down at the example, what I needed to do was I needed to first find r prime, and then I needed to, well, actually over here, I needed to find its magnitude. So then I had to find the magnitude of r prime of t, which was root 2, and then I had to divide r prime of t by its magnitude to normalize it to get us the unit tangent vector t. And then I had to differentiate that. Now, because the magnitude, this thing on the bottom, which ends up being the 1 over root 2, because that's a constant, it's not such a problem in this example, because when I differentiate, I just put that constant out front. But in other examples, r prime of t might not, or the magnitude of r prime of t might not be constant. It might not be a constant root 2. It might be some other function of t. And so this next step, differentiating the unit tangent vector, that could be a little bit more challenging because there's a scalar function out front and then the vector function as well. And you sort of have to maybe put the scalar in and then do a bunch of derivatives involving perhaps quotient rules, etc. So that's the challenging part. Here it didn't show up because it was a constant. The magnitude of r prime was a constant, but in practice it may show up. The nice thing about this formula is it doesn't depend on the unit tangent vector. It just depends on r, the vector valued function, its derivative and its second derivative. And so we don't have to worry about reparameterizing in terms of arc length or even finding the unit tangent vector, normalizing it or anything of that. It just, we can work it out just by taking two derivatives and then taking a cross product of them and working out the result. So very nice formula for the curvature. Let's prove that we do indeed have this formula for the curvature. The way we're going to prove it is I'll just scroll back up to this previous formula, this one here. What I'm going to do is I'm just going to work out an alternate expression for that top, t prime of t. If I can work out an expression for that top involving r prime and r double prime, then we will have reduced the dependence of the formula on t prime and instead re-expressed it to just depend on r prime and r double prime. So that's our goal, is to try to find an alternate expression for t prime of t, so the derivative of the unit tangent vector. So in order to do that, we first start with what the unit tangent vector is. It's r prime over the magnitude of r prime. Another way to write that is, well, we can say r prime, and I'll put the t's in here because these are functions of t. I just left them off in the first expression. So r prime of t, that is the scalar multiple magnitude of r prime of t times the unit tangent vector. Right? Just multiply through by the denominator on both sides, and we get this expression. We do have an alternate expression for what this is, an alternate way to write it in terms of arc length. So it's ds dt times the unit tangent vector, t of t. And that turns out to be quite a useful result. So let's just jot this one down. This is the useful part. Let's maybe call that star. And the reason is because in this next line, I am going to differentiate it with respect to t. Now, why am I going to do that? Well, you'll see why. I'm taking its derivative more from a geometric perspective than anything else, and we'll see why in the next line. So The derivative is going to be, it's a product rule. There's two pieces here. There's a scalar piece and a vector piece. And so the product rule says it's the derivative of the first. So this is now a second derivative times the second plus the first times the derivative of the second. Okay, and I said the reason we're going to do this is from a geometric perspective. The idea is that this piece is, so we've just decomposed r double prime of t into two pieces. If you want to think, I mean, sometimes it's helpful if you want to get like an application in mind where these things sort of represent objects that you're more familiar with. Think of r of t as just the position of a particle as it's traveling in space at a given time t. So r prime of t would be the velocity vector at any given time. R double prime of t is an acceleration vector. So this would be like the acceleration at a given point on the curve. And what we've done is we've just decomposed the acceleration into two different directions, a tangential direction and this derivative of the tangential direction, this t prime direction. So this is parallel to r prime, right? I mean, t is a unit tangent vector, so it's just r prime scaled so that it's unit length. So it's quite clear that it is parallel to r prime because it's just the normalized version of r prime. The other part, though, this may be the surprising fact, is that this is perpendicular to t and hence r prime, because r prime and t are parallel. So if it's perpendicular to t, it's perpendicular to r prime because r prime and t point in the same direction. So this is perpendicular to r prime. So we got a component that's parallel to r prime and a component perpendicular to r prime. Now you may say, well, why is this perpendicular to r prime? Well, it has to do with the fact that t is a unit vector. So the reason is because t dot t is equal to 1. And so if I differentiate this formula, if I take its derivative with respect to t, so these capital T's are functions of little t. So if I differentiate it, I get the derivative of the first times this, or dot the second, plus the first, which is t, dot the second, which is t prime. But t and t prime, you can dot them in either order. So this actually turns out to be just twice t prime dot t, and that's equal to 0. So that tells us that t prime is perpendicular to t. So because t is a unit vector, when you take its dot product with itself, maybe I should say it the other way. Because t prime is always a unit vector for any given t, its derivative is perpendicular to itself. That's what we've shown here. So we get this, that is perpendicular to t. And this part is parallel to t. So that's the geometry. That's why I've taken the second derivative, is because I've now done a decomposition of something into two pieces, a parallel and a perpendicular direction to r prime. And that's nice because if I take the cross product of these two things, because I've already split the second one into two pieces, something that's parallel and something that's perpendicular, only the perpendicular part will survive, because r prime cross r prime is 0. A vector crossed with itself is 0. So this means only the second one survives. Only the cross product of these two. And this is ds dt times t. Right? That's again using star, that formula up above. And so what this is I can pull the scalars out front. That's the ds dt squared now. There was a scalar in front of each of those vectors in the cross product, so I pull both of them out front. And that gives me a t cross t prime. And that's nice because t cross t prime, well, they're perpendicular to each other. So their magnitude is just the product of their magnitudes. The angle between them is 90 degrees. And so sine of 90 degrees, or pi by 2 radians, is 1. So there's a very nice result when I take their magnitudes. This is equal to ds dt squared, magnitude of t cross t prime, and that's ds dt squared, magnitude of t times the magnitude of t prime times sine of the angle between them, but they're perpendicular, so that's 1. The magnitude of t is 1. The magnitude of t prime, what is that? Well, that's the thing we're trying to find. Let's scroll back up. All right, that's that green arrow there. That's the thing I'm trying to find. I want to find an expression for t prime. And now I've got an equation that it sits in, which I can now solve. So we are going to solve for this part here. One more thing before I do the solve is I notice that ds dt, that's r prime of t. That's just another way of writing the magnitude of r prime of t. So I got that squared. And I've got this expression here. For some reason, the pen must have run out of ink because it's having a problem drawing that last vertical bar. All right, move that. There it is. Somehow it was hiding behind something. Okay, so there we go. There's our expression that involves t prime. We can now solve for it. So I get t prime is equal to r prime cross r double prime all over r prime squared. I'm leaving off the arguments of these are all functions of t just because it's going to make it a little bit more cumbersome to write. And we're pretty much done because now the curvature at a given t is given by the derivative of the unit tangent vector over r prime of t. That's the formula that we had up above. And that numerator is given by the expression on the left. And all we're doing is dividing by 1 more r prime of t. So that just bumps the denominator power up by 1. And so we get an r prime all cubed. And there is our result. So that's the end of our proof. Okay, so we've got an expression for curvature that just depends on r and its two derivatives. No having to rescale anything or reparameterize in terms of arc length. This is a nice formula that allows us to work out curvature. So let's look at an example. This is r prime, which is 3, 4 cos t, negative 4 sine t. We need to know r double prime as well, which is 0, negative 4 sine t, negative 4 cos t. We need to know the cross product. And the cross product, since I've written them stacked above each other, I can sort of imagine the I hat, j hat, k hat and this sort of determinant going on here. So I can start to piece together the individual pieces. So the first component is going to be negative 16 cos squared t minus 16 sine squared t. So that's the 2 by 2 determinant of the left or the right part, the middle component and the right-hand component. And then just work my way across. The next one is going to be 12 cos t, and the next component is going to be negative 12 sine t. And so the magnitude of that is going to be the square root of, well, we notice that this thing, that simplifies down to just negative 16. So that's going to be 16 squared plus 12 cos squared plus 12 squared cos squared plus 12 squared sine squared. Again, cos squared plus sine squared is 1, so that gives us a plus 12 squared. And there's nothing on the bottom. And so that's a root 400 or 20. And so the curvature of t is given by this cross product in magnitude all over the cube of the magnitude of r prime of t. So that's 20 the magnitude of r prime of t, I might as well write it out here, r prime of t is 3 squared plus 4 squared cos squared plus 4 squared sine squared, so that's 4 squared, which is root 25 or 5, so it's 20 over 5 cubed. We get a 5 canceling, so this is 4 25ths. And so there we go. That's an application of that last formula. Again, it was simpler in the sense that we didn't have to work out the unit tangent vector and then differentiate that. In this case, probably wouldn't have been so bad again because, again, the derivative of r is a constant. But in more complicated cases where the derivative of r in magnitude, the magnitude of it is not a constant, so it's not a constant tangent vector at each point, then it becomes harder to use the previous formula, and so this one involving the cross product is simpler. All right, so that should give you enough to do any of the remaining questions that you perhaps would have tried to use the other formula on, which would have been a little bit more complicated. This one could allow you to do it by bypassing the unit tangent vector. All right, have a good weekend, everyone, and have a good reading week.